A very good morning to one and all. A warm welcome to all our participants for today's webinar on the evolution of Spotify's mobile home architecture. We have with us the resource person for today's webinar, Mr. Rajesh Chennai, who is based in Spotify at New York City. So he also happens to be one of the proud alumnus from the Department of Computer Science and Engineering, Vidyavardhaka College of Engineering. I now request Professor Radhika to briefly introduce our today's resource person for the webinar. Over to you, Radhika.
Good morning, everyone. I take this pleasure and opportunity to introduce Mr. Rajesh Chennai. Mr. Rajesh Chennai is a proud alumnus of VVCE, graduating with Bachelor's of Computer Science and Engineering in the year 2008. While he was in VVCE, he helped in organizing Tech Talks, and he also was a part of Department and College Fest and won the Best Student Achiever Award in the graduating year of 2008. He went on to study at NCSU, Raleigh, and graduated with a master's degree in computer science in 2009. He began his career working in embedded software development, working on Garmin OEM systems for Toyota and Packard trucks. In 2011, he joined JP Morgan's investment banking division, writing a state-of-the-art, scalable, low-latency pricing engine that computed interest rates curves within milliseconds. In 2015, he joined a nascent startup TimeHop as a senior backend engineer, where he helped scale services from 3 million to 42 million daily active users. In 2017, he joined Spotify, where he helped scale home from 50 million to 300 monthly active users, and it is still growing. As a staff engineer at Spotify, he writes code, architect backend system, guide product direction, and mentor several engineers. We are very happy and proud to have you here with us, sir. Please start the session with your presentation.
Thank you, ma'am. And welcome everyone to today's session. I'll be speaking about the evolution of Spotify's mobile home architecture. Thank you for having me. And yeah, Vidyavardhaka is the college I graduated from. Have very fond memories, and it's great to be back. Ma'am has already introduced me, so I won't go through this slide. And yeah, so Spotify, what we do at our core is we try to bridge the gap between artists and fans. We try to get the artists. We try to help artists live off their art and help fans discover and listen to their to familiar songs and tracks and audio, like even podcasts. So this is our mission statement. Our mission is to unlock the potential of human creativity by giving 1 million creative artists the opportunity to live off their art and billions of fans the opportunity to enjoy and be inspired by it. Some stats about our company: we have about 140 million subscribers, paid subscribers, 300 million monthly active users, about 15 billion in revenue has been paid out to rights holders. 92 markets is where we are active, 60 million plus tracks in our system, 1.5 million podcast titles, and 4 billion plus playlists. It's a huge operation behind the scenes, behind that small app that you have on your phone. So today we'll be speaking about what do I mean by Spotify Home, how we got started, what we experimented with, like Word2Vec and batch pipelines. We'll try to get into some of the details about Word2Vec. From there, we'll talk about how we move to real-time recommendations using microservices. And lastly, the sweet spot that we found by achieving near real-time recommendations by using streaming pipelines. I'll try to get into certain technologies that we use, and hopefully that'll give you some insight into how we've architected the system and how this system has evolved over, 4 or 5 years now. So Home is the primary tab on the Spotify mobile app. This is where most users come in to get their familiar content and to discover new artists. When I say familiar content, you can listen to music, you can also listen to podcasts and audio, and there's other formats that we have. This is hyper personalized. So this space is personalized for you, for your taste. It depends on what you listen to, and our algorithms are pretty efficient at suggesting new tracks for you to listen to, for example. So within home, we have this notion of shelves and cards. So home is a collection of shelves, and they're organized in a stack manner. So you have the top shelf and the next one and the next one. There's about 20 or 40 shelves, and each of these shelves has a number of cards on them. And what we do is we personalize this content. We generate these shelves. We have algorithms to cater to different content hypotheses. You have podcasts you want to listen to. You have more like the artists you just listened to. You have your favorite artists. You have the shortcuts or the favorite stuff that you've listened to in this past week. That's at the top. There's also recently played. So all of this is very personalized, and we use algorithms to curate this experience for you. But this wasn't how it used to be. When Spotify's first iOS app was launched, there was no home screen. If you see the screen grab from 2016, I think, we can see there's a search bar, so you can search for songs that you want to listen to. You have a browse tab. You can go in and look at different genres, and you can select music you want to listen to. You can go to the radio tab and play music that's similar to something, a seed track or artist, if you will. And your music is where we save your favorite artists and tracks and playlists that you've liked. So when we first added home to the app, it was made up of very generic and static shelves. These were human curated, and there were no algorithms involved. We have a lot of editors. They would go in and curate different shelves, and the differentiation between any two homes is only regional. So everyone within a particular region, like the US, would see a very similar homepage, and it was not personalized at all. It didn't cater to your tastes. And our team was tasked with making this personalized and making this experience better. So what we started with was batch pipelines. And what we wanted to do is take your listening history. We know what you listen to, try and generate some vectors along with this listening history, and then recommend these playlists in batch pipelines. We wanted to try a single shelf out. Can we create a single shelf that's personalized to a user's taste, to a user's listening taste? So how that works is we have certain data sets, your listening history data sets. We generate some vectors using this listening history and artist relationships. And these go into Hadoop jobs, which would then process all of that big data and store it in Cassandra. On the other side, when the user opened their app, it would go into this configuration management system we have, ping the reader service that interfaced with this database, and then fetch that content and render it on your home screen. We can get into how we generate these vector files. The way we generate vectors is using word2vec. So what is word2vec? It is a technique that's used in natural language processing. And what it is you train a neural network and try to find word associations. So you have a corpus of text, you break it down into tokens, and then you train this algorithm to say, here's this token, how is it associated with other text that appears right next to it? So certain examples of what it can do is when you give it some partial input, it can predict what relationship it has with another word. For example, you can talk about gender. You can give it king, it'll give you queen. You give man, it'll say woman. You can also use verbs. For example, walking, it'll give you walked. Swimming, swam. The present and past tense. It can associate countries and capitals: Spain, Madrid, Italy, Rome, and so on. Of course, all of this depends on the corpus of text that you give it, and how you train that data. How is this associated with playlists and tracks, though? Well, playlists are made up of similar tracks, and tracks can appear in multiple playlists. So we can find associations between different tracks and how these tracks relate to different playlists. You can break it down into saying the playlist is a paragraph and each track, for example, is the word, right? So this is one part of that equation. The other part of that equation is nearest neighbors. You need a way to represent these vectors. And the way we do this is using annoy trees, which is approximate nearest neighbors. There's a library that someone at Spotify wrote, which you can check out. And this is a visual representation of how these vectors show up. Any two artists that are very closely related will show up in, for example, that pink section down there where A.R. Rahman and Pritham are pretty closely related. On the other side, there's Pink Floyd, which I don't think is really related to A.R. Rahman, right? So there, it's in a different section. And the reason this library is pretty good is because it's pretty fast and memory efficient. We don't need to find the exact nearest neighbor. We want to just do a good enough job to find what's in that cluster of or cluster grouping of tracks. And so the way these batch pipelines worked was you take these playlists and tracks, you feed it into Word2Vec, generate these vectors and have annoy trees and give it this listening history to kind of generate recommendations, which works well, pretty well. And but it has some drawbacks, right? So when you do batch pipelines and serve it in such a way, it gives you very low latency, which is great. You can, in case there's a problem with the pipeline, maybe a data set is late, so the pipeline didn't run today, you can always fall back to the previous set that was generated yesterday. That said, the recommendations are pretty stale because they take about, if this pipeline runs once a day, you have recommendations that are updated only once a day. So if the pipeline has failed and we're serving you something that we're falling back to, you're getting recommendations that are at least 2 days old. The other thing that was very hard in this type of approach was experimentation. So we couldn't generate two shelves and see how users reacted to one algorithm versus the other. So this type of experimentation was very hard to do given the long cycles in generating these recommendations for 50 million users. Also, within the system, we have to build and maintain our own Cassandra and Hadoop clusters, and that operational overhead is pretty painful. So what we did was we wanted to say, okay, we've got the basics here. Can we make this better? Can we make this? Can we write more shells? Can we make this faster? And microservices is all the rage. So we said, let's take this and put this on the user path. Let's convert these things into services. And so the listening history, we converted that to a service. We got the vectors into files and created that, made a service, and wrote a shelf generator that did this in real time. So when a user loads their home screen, it would go into this configuration management system and fetch the shelf from the shelf generator. It would be generated at request time. Now, as you can think, this could take up to 700 milliseconds. This used to take up to 700 milliseconds. And what happens is, as you want to add more shelves, we need to write more shelf generator services. This quickly adds up. So if you need 10 shelves, you have 10 microservices. And on the left-hand side, even though there's the listening history service and vector services, there's a lot more inputs that go into this. There's user data, there's track metadata, there's album metadata. There's a lot of stuff that goes into building a shelf. And so we ended up with a service sprawl of 10 or 15 services as we were adding new shelves to home. And that quickly became maintenance costs, on-call costs. So if something went down in the middle of the night, now you're up, it's not one problem, you got 10. And what we learned from that was real time is great. The updates being at request time means that when the user is loading home, they have very relevant recommendations. You just listen to something and we're able to say, here's something more like that track you just listened to. The stack, if you just saw the architecture diagram compared to the pipeline, it's pretty simple. It's a few services just calling each other, microservice mesh. It's pretty standard in the industry these days. It's pretty easy to develop and experiment also. Given their services, if you just want to replace one shelf with another, just call a different endpoint and that'll give you a different shelf. Compared to the batch pipeline, this is low maintenance. That said, it still had pretty high on-call overload. What this failed at was high latency to load home itself. So when you have every service taking 700 milliseconds to try and generate recommendations and you have 10 of them, these latencies add up. Also, if we have a particular shelf and it's generated on the request path, we have nothing to fall back to. There was no yesterday's recommendation. So if all your services failed, you'd get an empty home, which isn't really a great experience for users, right? So we said, you know what, we want to write many shelves and we want this to be fast. And for that, we ended up with the solution for real-time streaming. This was also the same time when Spotify was moving its infrastructure from on-prem to Google Cloud. This was a great advantage because now you had all these tools at your disposal. There was the Cloud PubSub, Dataflow, Bigtable. We had a bunch of things that we could use and not worry about having to create our own clusters and manage them. So real-time streaming, this architecture works pretty simply, where what we want to do is listen to user actions. So every time you have the user listen to something, or you have track hearts, or you follow an artist, these are all user actions, right? And so there's a bunch of logs that are collected and then published into Google Cloud PubSub. I'll go deeper into each of these technologies and tell you how we use them. We publish them into PubSub. You have streaming pipelines that subscribe from that PubSub and write to another topic. So the reason we do this is because we have millions of signals, and not all of them will result in a high fidelity signal that we want to curate something for you. An example of this would be when you're listening to a playlist passively. We know that if you're listening to a playlist passively, and even though that's listening history, curating home for you is not going to really give you anything because you're not accessing it. You're probably running or you're doing something and listening to music. So these signals are not pretty good indicators of you visiting home. On the other hand, something where you just clicked a button and you said, I like this artist, is a more high fidelity signal. And so we have the first streaming pipelines to clean out and reduce the number of signals to high fidelity signals and publish that back to PubSub. From there, we use a bunch of other curation pipelines that we've written using the same code we wrote before for shelf generators, but now they all live in the same code base. And it's a pretty modular architecture there and easy to manage. So these curation pipelines, they generate these recommendations and write them to Bigtable. From Bigtable, they're served. So a user opens their app. Again, it goes to the CMS and reads a service and reads it from Bigtable. This is extremely low latency operation. These curation pipelines, they also subscribe to data sets and query data they need from other services like the vectors that we spoke about before, or your listening history or your favorites. So these things can go in and inform the content hypotheses for that particular show. So what is PubSub, right? PubSub is an asynchronous messaging service which decouples services that produce events from services that consume those events. So you can have these publishers that publish different events. Like, I like the song, I hearted an artist, I listened to the song, and they can go to different topics. And you can have subscribers that subscribe to those topics in different regions and then consume them. One way to think about PubSub is a highly distributed, highly efficient queue. So you could write different events on one side as the sink and subscribe to them on the other side and ensure that it's going to get to the other side, and then take that and process it. So we can use it as message-oriented middleware. You can use it in event ingestion. You can use it in computing analytics, for example. And it's very durable. You can store millions of messages and persist them for up to a week. So something that's coming in and you have traffic spikes, PubSub is a great way to neutralize those spikes. So you can write them, and PubSub acts as a buffer to your subscriber. The other piece of this puzzle is Dataflow. And Dataflow is this platform where you can code data pipelines, batch data pipelines, and streaming data pipelines. We don't use Dataflow directly, like we use Dataflow as the platform. What we use to write our pipelines is Apache Beam, which is a model in which you can code these pipelines. It's a pretty open source project, and you can use Beam to write pipelines for Spark and a bunch of other backends. We use it to run data pipelines on Dataflow. But someone within Spotify wrote a Scala API for Beam. So it's a wrapper around Beam, and Google Cloud, it's a wrapper around Beam, and we run Shio on Google Cloud Dataflow because Scala compiles to bytecode. So it's inspired by Apache Spark and Scala language, which are pioneers in this area. So why Scala? Why Shio, right? But before we go there, let's talk about what a pipeline does, what the basics of a pipeline are. So you read data from a source, you transform it, and you write data. That's what most pipelines do. There is a data set, there's a database where you get your source data, you can apply transforms, you can clean it, you can perform transactions on it, and then write that data to a sink. It's a different set of data. It can be BigQuery, it can be a file, but you can consume it somewhere else, right? And digging a little more deeper down into that, the source data that you transform result in what you call a P collection. A P collection is named as such because the P stands for paddle. And every transform you do results in an immutable collection. And these are highly parallel. So every stage feeds into the next stage, where you take this data, transform it, there's a P collection, then you can apply a transform, and then it goes into sync. So this is how like a basic SHEO job looks like, and this is how most of our pipelines look like. It's a little more complicated than this because it uses a bunch of other data. This is an example of how you can do SQL word counts on a text file, for example. And it also is an example of how data jobs are pretty fit well into the functional paradigm, right? So you're taking a text file and then you're splitting it into tokens, deleting the non-empty tokens, and then flattening that down into a list, following which you count and save the output as a text file, right? So I'd recommend checking this library out to write data pipelines. It's a pretty nifty library. The last piece of that puzzle is Google Cloud Bigtable. And the way I want to think, or I usually think about Bigtable, is a highly scalable hash map, a super huge, massive hash map. There's a key and there's values, and it does a great job of that. Well, it stores this data as a sparse, distributed, multi-dimensional sorted map internally, and it's non-relational. So it's no SQL. You don't have to deal with tables. You don't have to deal with relations between data. It's quite simply key and value, and it's very low latency. It's also very easy to scale because you can just add nodes into the cluster. You can just go into Google Console, add nodes, and it increases. It scales. So how do we do the schema design for Bigtable? Bigtable allows rows to contain multiple values spread across different column families and column qualifiers within those families. So what do we mean by this? There's a particular row key. It can be some sort of unique identifier. And the next namespace in that row key is a column family. Within that column family, you can have many columns and many values. And this is just one level. Beyond that, you can also have versions. So in every column and value, you can have versions of those values. So you can timestamp versions of those values. So you can fetch something that was previously written as long as you store it. This is, for example, how we've designed our database. There's a user key and recommendations like family, and every column is a type of recommendation. And within each type of recommendation, we store the set that we just curated for you. There's a bunch of playlists or artists, or a combination of playlists and artists and tracks. It depends on what that shelf is supposed to be. So if we piece this back together, we can see how there's user actions. They flow into PubSub, this massive queue, which can consume a lot of data. There's a streaming pipeline that's consuming from that PubSub and cleaning that data and reducing it into a smaller data set. That's written to another PubSub topic, which is consumed by another pipeline, right? Which does a lot of the heavy lifting of generating these recommendations and then storing it in this recommendations Bigtable. On the other end, again, we have a simple, a dead simple service that reads from this recommendation and gives this gives the shelf out to home. Now, when we did this, when we ended up with this architecture, what we were able to do was write many shelves. We wrote, I don't know, there's about 60 shelves now that are generated by this method. And we reduced the amount of time it took to write a shelf from 2 to 3 weeks to 1 day. So we were just able to churn out many shelves. That gave rise to a very interesting problem, which is now you have 60 shelves. How do we tune that to the user? That's a talk. That's a whole session in of itself. where we use the user vector and a bunch of other inputs into our machine learning algorithm to rank these shelves based on what we think is best for that user at that given point in time. And there's a bunch of papers that have been written on it by my teammates, and you can ask me and I'll send you links to that. So when we did this, I think this is where we are today, and we really love where we are. The updates for any shelf are in near real time. So when we say real time, it's always good to understand how much real time is real time, right? So it can be the last second, it can be the last minute, it can be the last 5 minutes. And for us, about 5-10 minutes was pretty good, and it served the purpose. It's low latency because it's just like that Cassandra database or Bigtable, right? So it's a hash map. You just find the user key and get all that content. Fallbacks are easy given Google Cloud's Bigtable's cell versioning. So you can look at different versions of the cell. If we've not generated something for you now, we can always fall back to the previous version. There's always a value if we've curated anything for you. It's very low maintenance, right? We don't have to spin up our own servers for anything. We don't have to manage our own clusters. The stack is pretty modular. That said, what we design has a lot of moving parts as compared to the other two systems that are pretty simple. But then there's no pain without gain. These are all trade-offs. If you want super low latency, then we need to go to pipelines and data pipelines. If you want real timeness, you want to go to services. So it's always a trade-off between one or the other. The key takeaways are that managed infrastructure is always great. Not having to deal with configuration is amazing. You can focus on the product. I remember the LAMP days that we used to have long ago. We'd have to create our own server, you install Linux and MySQL, and those days are gone. You just click a button, you have the service that you need, and you can run your application. Streaming pipelines and Cloud Bigtable are a great combination for near real-time use cases. Keep in mind, a friend of mine long ago mentioned that programming is just loops and hash maps. I still am thinking about what he said, but it kind of is true. Bigtable is a big hash map and makes life very easy. Also, when we were doing all of this, our main use case was user delight, but also on our end, we wanted to make sure developers could be productive. If developers are stuck in day-to-day activities like on-call and maintenance, it gets really hard to focus on product and experimentation. So optimizing for that made it really easy for us to iterate and scale this particular architecture. So yeah, so that was the talk. I want to stop for questions if you have any. If you have any questions, you can type them in the chat box and I'll be able to read them. don't think there are any major questions. Abhishek, yeah. So yeah, that was the talk. So if you have any questions, reach out to me and I'll be glad to help you out. And
Hello, Rajesh.
yes, ma'am.
Rajesh, you can as well take up few of the common queries probably our students would be exposed to with respect to the mobile home architectures. We don't
Sure.
have specific questions.
There's no specific questions, right? Yeah, I mean, I'm struggling to find questions because I'm very used to this architecture. So, I mean, do people want to hear about how to write PubSub or Dataflow or Bigtable, for example? We can go over to Vec again and how that works.
Apart from that, what are the common suggestions from your side to our upcoming graduates in this particular area? What are few of the challenges they see forward?
Right. So I remember from my studies, like the things that I was being taught, during college, it was like SQL and LAMP and Java and C Sharp. These days, all of that they're all used, but there's higher level abstractions that make your job way easier. So you never have to set up your database anymore. There is a Google or AWS offering where you can go in and press a button and the table's there. You might have to write some scripts, but there's a bunch of libraries and tools that make your life way easier. And I would say choose that path because then you can focus on your product. There's there's a lot of young people that want to start startups, right? So they'll face these same problems when they're scaling. They'll need ways to figure out how to scale to traffic. When they start, they'll have, I don't know, 10, 15, 20 users, which is easy. You can write a service. You can use this microservice design that we mentioned here, right? Sorry. Yeah, it'll look something like this. You have the request coming in, you have a service, and you can generate these in real time. And for the most part, this will work. But as you scale to thousands and more than a million users, this starts breaking down. So at that point, you start saying, okay, what are the trade-offs I want to make? And based on those trade-offs, you can use different tools. You can use queues, PubSub. You can use data pipelines and data sets. You can use Bigtable for caching. Bigtable has many use cases. One of these use cases is to cache data. It can be also used to store intermediate data. It lends itself as a low latency system that fits into many architectures. So it's always about trade-offs, and when you're designing a system, design it in a modular way where you can always take something out and replace it with something that can scale.
What are the specific opportunities you have with respect to Google Bigtable, because it's taking a huge trend these days?
Yeah, so Bigtable is a great technology to learn and use. It's also very simple. If you think about that abstraction as a hash map, we've all written Java programs with a hash map. And sure, it's not just the hash map. There's a lot of things that are going on underneath the hood. It's very distributed. It works across regions. There's replication. So, but you need to understand these concepts. But these are not concepts you're going to use when designing your application. The abstraction is that there's Bigtable and there's a key value store. So when you use the API, all you're going to do is say, okay, store this key and this value in this location, and in the other side, you're just going to say, given this key, give me the value. There's a lot of opportunities like to learn and create architecture that scales. Many, but it always depends on the kind of the kind of use cases, right? So every use case has its own trade-off. There may be use cases where you definitely need real time, and in that case, you want to add more nodes to your microservice architecture. On the other hand, if near real time is okay for you, then you can use Bigtable to serve a bunch of data. Does that answer your question?
Common employment opportunities for our young graduates.
Yeah, I mean these. So if you learn AWS, I mean this is a suggestion for everyone graduating now. Is that you don't have to learn everything, but you should be familiar with AWS or Google Cloud or Microsoft Azure. You would need to know what these systems are. They all have very similar abstractions. For example, there's Google Cloud Bigtable. There's also DynamoDB on AWS's end, which is similar. It's not the same technology, but it's again a key value pair with which is NoSQL. Microsoft has their own version of it, so you don't need to learn all three because it's impossible, and you don't need to be an expert in either one. In any one, what you need to do is use these. Choose one of them and learn and write applications that teach you these different systems. I think Google has some credits that they give for students, so they can always like create a project when they're doing their final year or sixth year project. I don't know if they still do that, but when they're doing that, they can use these technologies to create those applications. And I think every company these days uses one of these three companies, right? One of these three large cloud service providers.
Rajesh, we have a question coming from one of our alumnus again. For someone starting in the scalable applications, how much of time should I spend on the DevOps aspect?
Right. So that would depend on what you want to do and your personal interests. There are people who love DevOps and who love infrastructure, and there's people who love writing applications and product features. So if you join a product company, for example, Walmart or Flipkart or Amazon, and you're in a product team, right? So they have many teams. You can join a product team. The product team is going to work on user-facing product features. And in this case, you're going to be using what the infrastructure teams give you. The infrastructure teams try and make it very easy for feature teams to work. And that is what I do. I work in the feature team. So I don't have to create many libraries that other developers are going to use. But if you're in an infrastructure team, your primary user are other engineers. We have a team within Spotify that their sole job is to maintain Kubernetes clusters, create Docker containers, create libraries that make it extremely easy for us to do our job. These days, we can just go in, click a button, and we have a fully functioning backend system that it's already done the Git commit, it's done the registration and everything, and it's there, and we just have to write our code to say, okay, this is the input we want, this is what we transform we want to do and write. So I think that is where the industry is headed. So if you look at AWS Lambda and Cloud Functions, for example, they're all serverless. There's no infrastructure involved at all. This is way different from what it used to be when I graduated in 2008, right? We needed our own server. You needed to shop for a server, install the LAMP stack, and do all these things. That's no longer the case. You go in, you write your code in JavaScript or Golang or whatever it is, and you press a button, and your service is live. So depending on your interests, you want to spend time in that particular area. If you really like configuration of services and scaling services, then you can focus on DevOps. If you like writing features and you want to create applications, you're trying to create a startup that services a particular need, then focus on the feature part of it and let the cloud providers handle most of what you do.
Okay, we have a last question. What are some of the technologies one has to learn for you to come up with a world-class application?
Ooh, that's a tough one. You don't really need. I mean, it's a very broad question. The world-class application part of it. You can, whenever you start out, you start small and you start with what you know. If you know Java, then that is what you should use to create your application. Don't spend time saying, okay, they're using C#.NET, so we should do it in C#.NET. What you know is the world-class technology that you will use to create your world-class application. Everything else will happen along the way as you solve problems. As you write that application, you write it, you figure out, okay, now I need a database. Where do I find it? Now I need something. Where do I find it? And most of these technologies are on par with each other. They're all priced pretty competitively. So it's not like you learn Google because that's 100 times cheaper than AWS. They're all pretty much the same. At least I think so. For the scales we are talking about. So just pick one of them, and any one of these cloud providers have tutorials on them. They have videos on how to use these in different use cases. There's examples out there. There's tons of resources on how to use these tools to create to scale your application.
Okay, thank you, Rajesh. We don't see any more questions as such. Thank you so much for sparing your precious time to be with us during the odd hours for today, in fact. Thank you so much. I also would remain thankful to the management, principal, HOD, and the entire Department of Computer Science and Engineering for having extended their full-fledged support in organizing this webinar. Thanks, one and all. Thanks, big thanks to all of our audience for today's webinar. Thank you, Rajesh, once again. Thank you so much.
Anytime. Yes, thank you.